Hello. Hello, everyone. How was your midterm? Anything surprising? A lot of students are not coming today. I'm not sure why. Okay, so starting today, we are going to look into the videos. We have seen image applications so far, mostly on image classifications and segmentations and object detections. So from today, we will apply the similar techniques to the video applications, which are quite similar, but it's a little bit more complicated. So we'll look into that today. Before we start, any questions? Any questions about the midterm or anything? By the way, I heard that many of you are struggling with the homework too. So we are extending the deadline by 2 days. So it will be, it might be already announced by the TA. So it will be due on Sunday, 11 a.m., just 48 hours extended from the original deadline. Hope that's helpful for you. Okay, so let's start today's lecture, the video classification, the first part. We have seen this slide in the very first day. You may remember that for computers or machines, a video is actually just a sequence of the images. And each image is just composed of a two-dimensional matrix of the pixels. And each pixel is represented with 3 or 4 values, like integer values like this, like RGB codes. So for computers, video is just a sequence of bunch of numbers like this. And our humans' understanding about videos is something like some high-level understanding of these scenes, like figure skating or winter sports, ice rink, or pair skating. So video understanding was defined as learning some function or developing some functions, mapping these two different worlds, how machine understand the video and how human understand the video. So in general, we define the video understanding task as this. And as its first specific application, we are going to see video classification today. So let's explore some more about the video understanding task first. So video classification is another name of action recognition. Similar to, it's analogous to the image classification is a different name of object recognition. So here, the input is given a video. We would like to classify the entire video to a predefined set of labels. And here, usually, the label sets are focusing more on the action sides. Still, we can find the objects within the video because it's just a sequence of images. So still, we can do the object recognition, but it's less interesting. Using the video data set, what we would like to focus more on is its actions or activities within the video. So yeah, in image applications, the labels were mostly objects, but here, videos, we usually need to recognize both objects and actions. So for example, this is not just basketball or sports games, but this is specifically slam dunk. So it's labeled with like the dunk shot or slam dunk. And this is swimming, but not just swimming, but we may also label it as a freestyle, more detailed and fine-grained class based on the actions we can observe from the video. So we are going to start with this video classification, but there are a bunch of other interesting video understanding tasks. One is video retriever or video search. So for retriever, we have a query which is given in a variety of forms. For example, if the query is text, then that is what we usually call video search. So we give some text queries like this, 2022 World Cup, and then we can see the related videos to this query on some web search engines like Google. Or the query can be another form, like another video. The query is a video, then what would be the task? We would like to retrieve relevant or similar or somehow related videos. So we can see such an example in Netflix or YouTube. When you watch some video, and at the end of that, it automatically plays something relevant to it, right? So that is called watch next, and it can be seen as from the computer's perspective. That video the user is currently watching on is the query, and we would like to recommend the related videos, and that is the watch next task, which is also can be seen as a video retriever task. Or a user or person or an account can be the query. So here, not related to the current video that they are watching, but given just a specific user's taste, we would like to recommend some videos that the user might be interested in watching. So all of these tasks are somehow related, just the form of the query is different. And we call them as a video retriever. And this is more, usually, this is more about topicality. So in the object recognition, we need to find the specific object within the image or in the video. But here, it's kind of less fine-grained, which means the main topic of the video, like the 2022 World Cup or soccer games. So it is important to capture the main theme of the video, and we'd like to recommend or retrieve the related videos from there. And as I told you, the video recommendation is a specific case of the video retriever task. So here it can be either personalized or not, but we are usually interested in more like personalized video recommendations or retriever, because each user has different tastes and interest. So we would like to recommend different set of videos to different users to maximize the viewership and eventually revenue of the company. So formally, the task is defined as considering the user's profile. This profile can be developed in different ways. And the context, this is really important in recommendations. Context may include who is the user and what is the current, when is the current time of the day, and which day, like is it Sunday or weekend or during the weekdays, or is it midnight or it's in the daytime. Depending on these contexts, or also which platform they are watching the video. Is it a smartphone or a computer? Depending on all of these kind of contexts, people actually enjoy different kinds of videos. So we'd like to retrieve the top N videos that the user may be interested in watching. And here we can consider a lot of contexts like the demographic information about the user, time of the day, platform, or previous watch history. All of these things can be considered. And this can or cannot be dependent on the current video. So if the user is watching this video, for example, we may make use of that information to recommend the next videos, or just user logged into YouTube system, and then the first scene looks like this, and then the user is not watching any video yet. So what should we recommend? So in that case, it's mostly based on the context and the user profiles. So video recommendation is really interesting task and really challenging task. So yeah, we may have some time to deal with some more about the recommendation stuff in one of our lectures later. And so far, it's more like understanding the main theme of the video. But now we are getting into more fine-grained understandings. So VQA, or video question answering, is or visual question answering on videos. It's a common task conducted in computer vision community. So we are given a video, and optionally it's script, or it can be also extracted using automatic speech recognition. And a question is given with natural language, and then our task is answering. So it's either multiple choices, or we have to generate some sentence or some words. So because video is is multimodal usually. It has the visual signal, audio signal, and textual signals based on the spoken language and the written language. A lot of clues is coming from different modes. So for example, in this particular example, these two guys, Sheldon and Leonard, they are talking in probably some house or something. I actually didn't watch this series, so I don't know. But they are talking about like, Leonardo, do you think I'm funny? No, do you? And they are just talking about themselves. And the question is, where are Sheldon and Leonard going? Which is not understandable if you just watch these subtitles. It can be only understood by understanding these visual scenes. So you can only answer by just recognizing where it is. And because I don't know the story, I don't know the answer. But some questions are the opposite. You have to understand the subtitles, not the visual scenes, because two characters may just talk to each other. We don't know. It's out of matter that where they are actually talking, but the contents of that is the key to the answers. So comprehensively understanding the entire scene, including the textual information and the visual information, is really important in this VQA task, which is really challenging but interesting task. And video prediction, it's another interesting task. So the input is a video clip, and you're given a video clip, and then we would like to generate the next frames given the current scene and current actions or current movements. And using our common sense and physics knowledge, what would be the next step, or what would be the next scene look like? So that is the video prediction task. So it's more useful when we apply to something like this, the climate change or the weather forecastings. So we have the climate variables collected in every hour or every 3 hours like this. And then after like 42 hours, what would this range look like after like 60 hours? So these kind of things were mostly done by environmental sciences or climate science using their own physical models. But nowadays, machine learning is taking it over. So it's much more efficient and more computationally efficient, and sometimes it's more accurate. So yeah, machine learning or deep neural networks are widely applied to these kind of tasks. And these tasks can be seen as an example of video prediction, because these are videos, basically, two-dimensional pixels with different channels. And we would like to understand how generally the pattern changes among these variables. And based on that knowledge we discovered from the data, we would like to generate the next scenes like this. And we can, for example, predict where the hurricane is going. So that's the video prediction. And another related task is unconditional video generation. So video prediction, we have a given video clip, and we need to predict what we're going to happen there. But unconditional video generation is just generating some video which look like real. So we're just given a random seed, and we generate a plausible video out of it. It's a kind of relevant but quite different task. And another task is the video compression and learning from compressed videos. So you may know that videos are like cumbersome in storage, right? Each image is, depending on its size, but its size is like megabytes, or hundreds of kilobytes to megabytes usually. But videos is a sequence of that. So if you just store all the frames in its raw form, then the size will be extremely large. So you cannot store the actual video in its raw form. But instead, there are a lot of video compression techniques which is applied to our current systems. So each video is compressed with very large times of, how should I say? So yeah, the compression rate is quite high. So it's compared to its original size, the compressed size is much, much smaller, like just 10% or 20%. So In that way, we can actually save a lot of storage. And when we only watch that the video, we decode it and actually play it, and then after that, it's just thrown away. But how should we compress them? So the basic algorithms are like this. If I give a lecture like this, my background is always almost the same, right? So we don't have to store all the pixel values as it is in this kind of lecture video. The only thing we need to store is my movement, or when I move slightly, then that needs to be captured. But the entire scene don't have to be stored as it is. So for each keyframe, which is one for every 10 or 15 frames, each keyframe is stored the entire pixels, but the rest of those frames will be just stored based on the difference between the most recent keyframe and its actual pixel value, something like that. That is the main idea, the basic idea of the video compression. And there are a lot of advanced video compression methods developed even before deep learning era. But nowadays, they would like to develop some machine learning-based models for video compression. So the goal is basically using the less disk space as much as possible with minimal loss of their quality. So here, for example, the original JPG looks like this, which is 800K kilobytes. But its 80% lossy compression is 38 kilobytes, much smaller. But you see that they are almost the same in quality. You can, if you see very closely, you may see some boxes pattern here, which was not shown here. But that's okay, because we are not interested in its background. We are more interested in this dog. And this dog looks really the same, almost. So for we can store, we can actually save a lot of disk space, but we can still store the key information of the image, and we can transmit it to other machines more efficiently. And in these days, very recently, within the last 2 or 3 years, there are some movements that we can try to build some video models based on this compressed video format, because the basic idea is actually capturing the movements of the objects, and we're just storing them. So why should we decode them? It's time-consuming and it's memory-consuming, and why should we do that? If we can just learn the model on its compressed version, then it's much more efficient in a lot of aspects, like the memory and the disk and the CPU and so on. So yeah, this is kind of new area, and as far as I remember, one of the team is interested in this for our class project. Yeah, so far we just explored what is the main video-related tasks, and let's see how they are challenging. So this is probably you can imagine easily why it is hard, but it's actually harder than you expected. So obviously, video is really huge in size. So storing the raw video requires huge storage cost, even if it's compressed. So for example, high quality movies is several gigabytes. And even though you have terabytes or petabytes of the disk space, but you can still store just thousands of them or just millions of them. Millions of them sounds large, but so anyway, storing raw videos is quite huge cost. And that means not just storing, but when we process them using machine learning models, we have to feed each frame, right? And if the video is long and if it's huge, that means it contains a lot of pixels, and we have to process them with our convolutional neural networks. As you may remember, in the images, we had to deal with convolutions on very large input image, and we have to convolve in all possible positions, and we stack all the layers, and that required a lot of computations. You have done that in your homeworks. So videos, we have n of them, n number of frames. So for very short videos, 3 seconds, still if the video is 30 FPS, then we have 90 of them for just 3-second long videos. What about for 1 hour or 2 hour long movies? Then yeah, you cannot imagine how much computation we have to have for these kind of video models. And also, because we have multiple images, but they are quite related, it's much more complex to model them, that spatial and temporal dynamics existing in the video. So that is the key of the video understanding, actually. We are going to learn how people are tackling those challenges. But this is really challenging still, computationally. So it is really common training a video model for like weeks to months, even at Google. So I've been working in video understanding team at Google since 2015. I moved to another team in like 2019. But during that time, that was the initial, the efforts to the video understanding was officially initialized during the time. And Google also struggled a lot to process all the videos on the YouTube. And which was like when I trained some models like this, for example, this is the picture I published in one of my paper in 2018 or 19, I guess. Yeah, 2019 on KDD. You see that this is just video level features were used, not the frame level features. Only the video level features were used to train some classification model. And it took like 50 hours, which is like over 2 days. And for this, you may be surprised that I actually used 10,000 computers to train this model. So if you have just like few computers or few GPUs, we cannot actually process these video models. So really complex and really computationally challenging, even at Google or similar companies. And that actually causes another issue. So because the video needs a lot of storage space, and that is not the end. Actually, we need to label them if you'd like to train some classification model for the videos. What is this video about? Is this about slam dunk, or it's swimming, or it's skiing or something? We have to label them, just as in the image classification task. And here, that means the rater actually has to watch the entire video. They might skip some time by time, but still they have to watch the entire video, which the time they need to take is linearly proportional to the length of the video. So labeling cost is much higher than images or text or other domains, which is actually, this is the hardest point. So people has to watch the video, and the labeling cost is huge. And it's hard to scale in terms of number of videos. Collecting like millions or billions of videos is prohibitively expensive. Not like the images. We can easily collect like billions of images, and we can store them in a hard disk without any problem. Videos, it's hard. But not just the number of videos, but the length of the video, like 2 seconds long videos versus like 2 hours long videos. Can we store like millions of videos with like 2 hour long movies? Storage-wise, it will be hard already. And the resolutions, we are no longer interested in like small videos like 160 times 120, which is very tiny videos like you guys on the screen. We are living in the era of like 4K videos, or I don't know. It's very, very huge, and a lot of pixels there, and we have to store them with a lot of storage cost. So scaling the video data set in all of these are really hard and challenging. And another thing makes us even more challenging is the copyright. Because it is harder to collect the videos and store it, we usually try to collect the videos from the web, because people share their own videos on the web, and we can easily download them as long as we have the space. But the problem is the copyright. So most video sharing platforms like YouTube doesn't have the copyright to hold the video. It belongs to the creator or the uploader. So they own the video, and if they decided to move it down, then no longer access to those videos. Which means if we collect like 100,000 of videos and create a data set, this is my 100K data set, and about a year later, people just decided to remove that from the website, and then other people cannot download those videos. And this data set no longer exists as its original form. In scientific world, we have to be able to compare against the baselines in a fair way, but as time goes, the number of videos in the data set will decrease. For example, I created YouTube 8 million in 2016, and now we have just 4 million plus videos. Just half of them are gone, even though they are the popular videos. So this is really hard to create some standard data set, and we'd like to keep its original form as much as possible, but because of the copyright, it's harder. And modeling-wise, the increased complexity is another challenging. So additional time dimension. We have the images, but now we have a sequence of them. So we have to model both spatial and temporal dynamics within the video. And also, the camera can move, or they maybe just concatenate with different clips to form even more complex videos like documentary. So all of these complexities needs to be considered, and capturing long context is another challenge. Probably if you are familiar with natural language processing, you have seen this a lot in their research community. So when the sentence gets longer, then how should we remember what was said or written in the earlier once we consume the entire sentence? The same thing happens with videos. Once you watch like 1 hour long video, do you remember all the details in the very first few minutes? Even human it's hard. But what we would like to do is not memorizing all the details within the video, but understanding the topics of the main theme of the video in the end. So we have to remember as much as we need from the beginning, in the intermediate, and at the end of the scene, at the end of the video. So we may take advantage of some internal structures, as I introduced in the very first lecture, but still it's really challenging, like capturing the longer context. And temporal resolution may be different video by video. So this is another minor issue. So if we build some model based on video collections with like 30 FPS, but now we have quality video with much smaller FPS, then how should we apply that? It's another relatively smaller challenge. So before we start our journey, I just want to mention that actually I'm working on this video related stuff in my lab. So I'm actually, I'd like to promote this research area. So I would like to say that what we see is a video. Human sees videos like visual scenes, not like a still image, but all the world is moving. And computer vision actually has focused only on the images so far, just because we are lack of the computation resources or storage resources. But it's obvious that if we can take advantage of the motions, we should be able to build even stronger models, and it should be possible if we have enough computing resources. But still, it's not like that. Still, the image classification model is outperforming the video-based models, just because we are lack of the computational resources. But people say that within 5 years, video-based models will surpass the image-based models' performance, even on the image classification task. Obviously, on the video classification task, it will be, because we are using more data. But even for image classification task, we can take advantage of the motions in our data set. So just a matter of time, but and the computational resource. But a lot of even simpler ideas were not tested well in this domain, and we will have a lot of things to do. So video research, yeah, there are a lot of blue oceans that we can explore. So by mentioning that, I would like to start the overview of how we tackle these video classification tasks in the last decade. Any questions so far? Yeah, I talked too much today because we don't have anything to review today, and this is just introduction. So I'm not asking any question and just talking by myself. Any questions so far? Probably not. Okay. So today and the next lecture, we are going to look into the action recognition task. And let's start with the very first ideas. The obvious baseline would be just using single frame. So given this short video clip, we just, as I mentioned it at the beginning, it's just a sequence of frames like this. And we just sample one of these frames. Then we feed it to some convolutional neural networks, as we done in image classification task. It will classify this particular frame. So it's just using the image-based model, basically. So the process is just simple. The video is just treated as an image by the sampled image. But the concept is obviously no benefit from a video. But this method is quite working well if the videos are relatively short, like a second or two, and the scene is homogeneous, like this. The entire scene contains very similar images only. Then this kind of simple baseline actually works. So the next idea is using multiple frames. So given this video, we sample frames. Suppose these 5 were sampled from out of like 30. And then we feed them to CNN, all of them. And then somehow we would like to get the distribution of these labels, but how? So that is the key question here. So let's see. How can we map from a sequence of frame level features to video level classes? So here, frame level feature means the features we are extracting from a single frame. So usually what we mean the very last layer, the bottleneck layer, as the frame level feature. But it can be actually any level if you'd like to. So all of these features are specific to this particular frame. And all of these features are specific to this particular frame, and so on. And then how can we aggregate those features to the score of the entire video? The video level features means we have just a single feature for the entire video. So one way of doing that is score fusion. So the entire CNN is applied only to the frame, and based on each frame, we have the score distribution, and then we take those score distribution to aggregate frame across the frames. Something like this. Each frame, we extract the feature, and then based on each feature, the classifier gives the score distribution like this. And then we somehow combine these. Somehow means usually average or max pooling. So from this, we see that this is figure skating, and this is also figure skating. Then we combine by like max pooling, and it's figure skating will be high score, right? So score fusion is the simplest way we can think of. Another way is feature fusion or earlier fusion. So frame level features are combined to video level features at some layer like this. Given these video frames, and then we extract the features, and suppose we extract the features until this level, then these vectors are representing the visual signals in this particular frame, and this one for this frame. And then we concatenate them or average them or max pool them, whatever. You just combine those features into one vector. And then you may add some additional fully connected layers to aggregate and output actually one score distribution out of that. So this is called feature fusion. And we have multiple options actually for doing that. So how can you aggregate frame level features? So these are what I just mentioned, the simplest ideas. So taking, suppose we have L frames from a given video, and then we extracted the features for each of those, x1, x2 to xl. And max fusion is just taking element-wise max over all of these vectors. So It sometimes works well. Or sometimes average works better. It depends on the data set or the problem. For average fusion, we easily just imagine, just add all of those and divide it by the length of the vector. Then it's the average fusion. And it computes the arithmetic mean of the frame level features. It's widely used, really simple, but strong. And another idea is concatenation, which is you just concatenate all of those frame level features. And optionally, but usually, you add some more additional fully connected layers to reduce the dimensionality. And then you will have one video level compact representation. This makes sense only when we can guarantee the number of input frames are the same. But it's usually not the case. I mean, some videos are like 2 minutes long. Some of them are like 5 minutes long. Then if you sample the frames with the same FPS, then the number of frames, which is the sequence length, will be different. And then when you concatenate them, then the dimension of those vectors will be different. So in that case, how can we train the additional fully connected layer on top of that? So you have to make sure that the input should be always the same length. But these are quite simple ideas you can easily imagine. Another idea is using the one-by-one convolutions. So suppose you concatenate them, but not like this, but stack them. So each of these vector represents each frame. But suppose you have 5 of them, then instead of concatenating end to end, you just stack like this so that each corresponding dimensions are on the same location like this. And then you can take, if you take the average over here, then that will be the same as average fusion. But instead of that, you can actually try one-by-one convolution to reduce the dimensionality from 5 to 1 or from L to 1. Then you can preserve the meaning of each dimensions, but still you can reduce the dimensions. And in this case, you can stack any number of frames, and then you can just apply the. It may not be true. Yeah, usually you use the same number of frames, even in this case, but it's less stricter than this concatenation part. So you can actually stack these number of a lot of frames, and then you can take the one-by-one convolution on top of that, and you can apply the same idea in the two-dimensional features. Like here, you may take some conv features like this instead of the flattened features like this. Here, then you can apply pixel by pixel dimension reduction using one-by-one conv to reduce the dimensionality like that. So these are, yes, Junho asked that is L the total frame length, and yes, that's right. I mentioned somewhere, I didn't mention, but yeah, this L is here, right? So yeah, aggregating the frame level features, we have these simpler ideas, but we can also apply like RNNs or some transformers or many other ideas later. But yeah, these are the most widely used simple ideas. And then, at which level should we aggregate frame level features? That's the next question. So one extreme answer is late fusion, the latest fusion. So from the video, we take a frame, and it is fed into some convnet. So it's just like ImageNet, image models. And then in the end, we have the frame level representation of that particular frame. Then we fuse them using the max, average, or concatenation or whatever. So in this case, we fuse these frames at the very last step of the feature extraction part. Or we can do the early fusion, which means at the very early step, we aggregate multiple frames, and then those aggregated vector is used as the representation of the video or the clip, and we just go with just a single feature like that. So here, let's see. This video has like 15 frames, but we take the 5 frames in the middle as our target or interest. and we feed them and represent these 5 features into one vector. So how should we implement that? In the previous part, we fed just one frame, which is one image. So it was same as our image models before. But now we are feeding 5 images. So how should we deal with this? This is a little bit different, right? So one way is taking just max or average to aggregate them first, and then just go with just one single representation. But that makes less sense because these are closer to the raw pixels or just raw pixels. And we have mentioned that taking the max or average at the pixel level doesn't make sense. Pixel level distance is not a good way of representing the images. We have talked about that at the very first part of our lectures, right? So what people suggested instead was 3D expanded convolutions. So extending the filters on the first conv layer to L times the feature size, the image size times the number of channels. So this is just image size, but we have L of them. But we can aggregate this by taking this L as treating these L as of features, the L channels. So these are 11 by 11 images and 3 channels for each of them, and we have 11 of them. But we rearrange them, or we just treat them as a sequence of 11 by 11 images, and we have 3 L of them. Now, within these 5 frames, we are kind of ignoring the order of those 5 frames. And we have 5 or L red components, and 5 green components, and 5 blue components. And all of them are considered as the channels here. So this L is multiplied here. So we have kind of 11 by 11 with 3 L channels. Do you understand this? Yeah. So early fusion, we take these as a channel-wise, and then we just feed them to reduce the channel. We can use the conv operations to freely adjust the number of channels to whatever numbers. So after that, it's the same as just image models. But the input takes just multiple images altogether. And we just talked about the late fusion and early fusion, but something in the middle is also possible, like this. So just as I told with the early fusion, we do the early fusion with different parts of the video. So each this video is segmented into like 4 parts, like this. And for each 4 parts, we take different 1, 2, 3, 4 frames to aggregate intermediates. And then they are also aggregated again and again, like that. So in this way, we can preserve the specific meaning or semantics within this particular time frame within the video until some level. So this is called slow fusion. So you can actually devise many different possible way of aggregations like this, but usually these are too complex, and just taking the average is slightly worse, but it's much faster in most cases. So this kind of slow fusion is less used recently. So from now on until the end of next lecture, we are going to go over all of these video classification models, the key models. Let me quickly overview the history. So this upper line is called two-stream approach. We're going to see what it is. So two-stream approach was started in University of Oxford by Andrew Zizerman. Professor Andrew Zizerman is now working at Google DeepMind at the same time. He started this line of research and contributed a lot to improve the two-stream-based approach. And this line, the bottom line, is one-stream approach, which is quite similar to what we've seen in the object recognition, but it's actually a little bit different. So there were 2 competing way of methods, two-stream versus one stream. And After this, actually, one stream started to outperforming the two stream approaches. And these guys adopted the ideas from this one stream approach, which is the 3D convolution operations, to combine these two. And now I3D and S3D becomes one of the standard. And Facebook was kind of more stick to the one stream approaches using the 3D convolution-like models, and they continued this line of research. So today, we are going to first see this two-stream approaches, and in the next lecture, we are going to see the rest of these. Okay. Let's see, why two-stream approaches? Here, we are learning about the video, which means spatio-temporal patterns. Spatial means spatial, and temporal means the time-wise dimensions. And this two-stream approach means they have one stream learning only the spatial pattern, just like the image models, and the other stream learning the temporal dynamics. Because the video is actually we have to assume that we are dealing with relatively short videos because this is 2014. They didn't have any GPUs like today's, and learning the entire long video was really challenging for them. So they did with relatively shorter video, like 3 seconds or 5 seconds, and that was usually captured by a single camera without any stops. So usually the visual scene is similar, and it contains just a single action, like shooting or like swimming, or I don't know. But it's basically the same action. Only one action was captured within each video. So the main idea is taking a single frame from the input, and this spatial stream convnet is just same as what we have learned so far, the image classification model, basically. So because this is single frame, nothing different. I think this is AlexNet-like model. They just fed this to have the softmax score. And the next one, the temporal stream, is quite different. This is similar convnet, but it has to deal with the temporal dynamics. So this is independent of appearance. So the input to this model is so-called optical flow. So what is optical flow? That's what we are going to learn today. So the definition of optical flow is this: distribution of apparent velocities of movements of brightness patterns in an image, which is harder to understand. So here, our interpretation is like this. Given two consecutive images, frame 1 and frame 2, the optical flow between them, which is defined pixel-wise, is given some part of this image where it is located. And the connecting vector is the optical flow. So suppose this point moves to here, this point, right? So the difference between the pixel index between these two is the definition of optical flow for that pixel. So something like this. On the right side, you can actually see the flow vector. Each of those pixels, if they don't move or they don't change the color, then it's almost like a spot like this here. But this satellite is slightly rotating to the right. So here, this optical flow map is colored. So if they move to the downside, then it's colored red. And if it's moving upside, then it's colored blue. So it's rotating like that. So this part is moving upward, this part is moving downward. Or you can actually see that the direction of those vectors here. So that is optical flow, and there's traditional way of computing these optical flows, and they have uses that. Let's take another example. So optical flow has two components, which is called U or V, or horizontal or vertical, because we have two-dimensional image. So in this image, for example, this car is taking the right turn here, and this means the horizontal-wise is moving to the left, and vertical-wise is moving to the upwards, right? So horizontal-wise, it's colored red, this car, and it's because it's moving to the upwards, it's colored blue here. So this U and V components captures where this each of these objects are actually moving. So you can see that these two cars are moving left, and this car is moving to the right. And the background is slightly red, but that's just the noise. And because these are the pixel-wise values, you can take the square of this and square of this and take the square root of that. Then that means that is the distance, the absolute distance of these movements. So if it's close to 0, then it will be black, and which is nothing moves significantly. But here you see that these 3 cars are moving, and where they are is more bright, which means they have higher values. And in this picture, they represented the actual direction of the vector for each positions. So this is the concept of the optical flow. And how do we compute the optical flow? I'm not going to the details of how we compute them, but let me just give you the basic idea of that. So we have 3 basic assumptions, which sounds obvious, but sometimes it's not true. So we have to think about this. Brightness constancy. So the same point of an object doesn't change its color significantly within the short time in the next frame. Basically, my shirt is something like blue or between green and blue. This color never changes significantly to red in the next frame, unless I have very specific lightning, like in karaoke. So this is the assumption that usually holds, that under brightness constancy, the color brightness values never changes significantly within the short time period. And temporal persistence means objects do not move far away in the next frame. Because suppose we are taking the video in 30 FPS, then the interval between 2 frames are 1/30 seconds. And no objects actually move that fast from here to there within that short periods, unless it's a UFO. So we are usually talking about humans or cars or buildings or something. So they don't move usually. And that is called temporal persistence. And spatial coherence means nearby points likely belong to the same objects. So my nose and my eyes are close to each other. And when I move my face, still they are close to each other. So nearby pixels move together or stay there together. But it's not like spreading unless it's like bombs. So there are some exceptions, as I told, but still most of these are usually held. And with sufficiently high FPS, all of these conditions are met in general. That's what I want to say. And there are several algorithms that we can take advantage of these assumptions to compute the optical flow. One of them is the Lucas-Kennedy algorithm. So I'm not going to explain the details what is the algorithm, but how can we just use that in OpenCV. So read actually 2 images. Suppose that the image 1 is moved to image 2 in the next frame. And here's the way of doing this. So from the first image, call this function good features to track. So this is, all of these are actually pre-deep learning era stuff. So somehow they extract some good points to track, which is usually the edges or some feature points of the image, not like the backgrounds or in the middle of the sea or in the middle of the backgrounds, but more like these some points that the color significantly changes, like this. And like the edge points. And this function gives the list of the points, which is in PT1. And then we give both images and PT1. Then this calculate optical flow function computes the location of the location of these PT1 points in PT2. So PT2 stores the coordinates of the corresponding points in the image 2 from the good features to track in the image 1. And then they actually draw both of them together. So this add weighted means they mix image 1 and image 2 half and half. So that's why they are overlapped like this. And this part is just drawing these points and representing the vectors. So you can actually try this code in some of these images, and you can actually try to capture the points to track. So somehow like this, but we are not going to the details of this optical flow computation. So let's come back to our two-stream approach. So spatial stream is the same as our 2D ConvNet image models, but the temporal stream is a little bit more complicated. So you see here that, interestingly, even though we are taking multiple images at the same time, the dimensions are still the same, right? These convolutional networks are exactly the same, the number of dimensions, which means it deals with each video just like the frames or images, just like this, the spatial stream. So how they do that? We've seen such an example like 10 minutes ago, right? So here we have, for each frame, we have two channels, U components and V components. We call that when we compute the optical flow, we have U channels and V channels. And for each frame, we have two. So, and we have L sequence, L frames. So in total, we have actually two L images, or the components, U and V components. Each of them are L sequences. So we just stack them as a sequence, and we treat them as entire 2L as a feature. As a channel, just as we discussed before. So with L frames, we have the number of channels is 2L, and each of these are the U and V components, and multiplied by the sequence length. And we treat them as if it's just 2L channeled image in the input. And after that, the number of channels is determined by the channels we decide here, which is 96, 256, and so on. So in this spatial stream, we take the 3-channeled image as input. And the temporal stream, we take 2L channeled image as input, but the rest of them is exactly the same. Okay? And this is more details, but optical flow stacking is we can just take the 2L images as is and just stack them. But trajectory stacking is more interesting. So one pixel is moving here to here in the next frame, and then it's moving on to here again, like to this way. And then the vector from frame 1 and frame 2 will like this. And what we are actually interested in is where this same points move in the next frame. So we'd like to just following the trajectory to add these vectors. So they still have the 2L channels, but the actual value is following its current location in each frame, so that we can actually track where it's going from the beginning to the end. So you can actually read the paper for more details, but the main difference is actually the optical flow stacking and the trajectory stacking is that we just stacking all of those as is the optical flow stacking. And if you just follow the trajectory to compute its current location, that is the trajectory stacking. But the size is still the same, it's 2L. And the two tower is fused at the scoring step. So each of these will output the score vector, and then they are aggregated using like max or average pooling at the end. Okay, the limitation of the two-stream approach. Long-range temporal information is missing here. So they actually did with very short videos. So this wasn't that serious problem, but yeah, this method is basically subject to, they cannot actually remember the long-range temporal information efficiently. And this is more serious problem, which is called farce labor assignment. So because they take only one image as its spatial information, and that was chosen randomly. So for example, this one, this is the input video. So you see that this athlete started running at the beginning and jump, and then yeah. So what is the label of this? This is long jump. But at the beginning of this video, it's just running, because you just see this scene. We cannot find out that this is long jump. You can only see that at this point. So if we just unfortunately randomly sample this particular frame as our spatial representation, we don't have any clue that this is long jump. And the model will be trained without that knowledge. But the label is long jump. And then this model will learn that this is about long jump, but that's just running. So this sparse label assignment is a big issue with this simple approach. And another thing was that we had to compute the optical flow, and we have to store them. So this is quite time consuming. And it also needs to store that long video, all the pixels, so it's costing storage, which is a big downside of using optical flow. But until that time, using the optical flow was the best way of capturing the temporal dynamics, so they couldn't get away that part. And train both streams separately, and no end-to-end train. So after a few years, the same author improved their two-stream models slightly. So here, actually, they tried to fuse the two streams in the middle instead of at the end. So before fusion, the two streams, the spatial stream and the temporal stream, are separately trained, and each of these layers have different values. But at some point, they fuse them using like max fusion or average fusion. And after that, they have only the common layers after that. So that was they have tried different parts to split the aggregate, and they also tried like this. Instead of having only one after that, they have the additional spatial layers, and they are also fused again later. Something like different architectures they have tried in this paper, and it was quite successful. But one more details we need to discuss here is that, see here, before they were training spatial stream and the temporal stream separately, and each of them just outputs the scores, and scores are the number of dimensionality is the number of vocabularies, and that's always the same. So they didn't have any problem. They can always aggregate them using any way. But here, they are fusing the features in the middle, which means if they would like to, for example, doing the max or average element-wise, input conv maps should be in the same shape, right? If they are, usually they are conv features with some two-dimensional map, feature map. And if they are in the different shape, then it's really tricky to combine them, right? So they intentionally matched the feature size in all layers like this. And then in any layer, they can actually combine or aggregate those features using max or average pixel-wise. So that was their strategy. So introducing pixel-wise correspondence between spatial and temporal features, as opposed to fuse only at the last classification layer. This is their main idea, and which was working quite well. Yeah, so you can actually refer to the paper for more details of this model. So the meaning of this paper was they have studied when and how to fuse two towers, both spatially and temporally. And they drew some conclusions, like when is the best time to doing that. So in general, their conclusion was fusing earlier than classification layer does not hurt the performance, but it saves a lot of model parameters. So you may remember that in our lecture 8, as far as I remember, ConvNet models have their parameters. Number of parameters are the largest at the beginning. No, at the end of the model, because of the fully connected layers. But because we share two of those models in the end, actually that saves a lot of space for those additional parameters. And that was one of the contribution of this paper. So usually having separate is beneficial. We have nothing to lose because it has more capacity in general, but they realized that earlier fusion actually doesn't hurt the performance, but fusing at the very first is also hurting the performance. So they suggested doing it sometime in the middle. And fusing at the last conv layer performed better than doing it earlier conv layers. So that's what they have discovered. So this paper is more about like experimental papers and exploratory on over different architectures, potential architectures, and yeah, they have discovered some interesting stuff like this, and I recommend reading this paper. And in the last 10 minutes, we are going to see the last model. TSN is the temporal segment networks. So this is an incremental improvement on the two-stream models, but actually they have quite interesting points. So for better long-range temporal modeling, they have sampled input snippets from k uniformly divided segments. So why do we want to do that? As I mentioned before, like this, we don't want to just rely on our luck to sample the right spatial information. So they sample multiple uniformly in the entire video. Then they learn the spatial representation from each of these images. Then they combine. So we are that kind of approach can be more robust to random picks. And in addition to optical flow, they introduced two more temporal streams, which is minor, warped optical flow or RGB difference. Yeah, you don't have to know all the details of these. And to reduce overfitting, they took advantage of up-to-date techniques. This paper was written in 2016, and the work probably has done in 2015, when these ideas like batch norm or pre-training or dropout, these ideas were proposed right before this work. So they took advantage of all of these to improve the model. So here's the network. It looks complex, but actually it's the same as before. So the entire video is split into k different parts, and each of those clips are fed into the model, and they choose one image as its representative and to learn the spatial information from there. But they have multiple of them, and they extract the optical flow, and using that they learn the temporal convnet. And in the end, the spatial convnets are aggregated together here to output the scores based on the spatial information. And the temporal convnets are also aggregated like that, and they have the score distribution based on the temporal convnets. And then eventually the score is aggregated to finer labels. But the main idea of this paper, yeah, that was just the main idea of that paper. Yeah, and the very last model is this one. Yeah, hidden two-stream. So I briefly mentioned that computing and storing the optical flow in advance is time-consuming and requiring a lot of storage cost. So people wanted to remove that part, but it wasn't possible for the few years because optical flow was too strong and too good way to represent the temporal dynamics, and it wasn't possible to beat the baselines if we don't use the optical flows. So people wanted to remove that, but it wasn't possible. So their idea was, instead of computing the optical flow in advance, they proposed to computing it on the fly. So this architecture is representing that. So spatial stream is the same as before. It's just CNN, the image models. And this part is same as before, the temporal stream CNN. It takes the optical flow as input and output the scores, and they fuse the scores. But now they add this motion net here. Motion net is given the raw images or the raw video. It outputs the estimated optical flow so that this temporal stream can consume that. So the idea is that given two consecutive images, it estimates the difference between them. So they use the reconstruction loss. The optical flow should satisfy this condition. Given the next image in the second frame, subtracted by the optical flow, then it needs to be similar to the first frame. That's the definition of the optical flow, right? If you move it to here, and then it's I2 minus I1. So we know the I1 and I2 here, 2 consecutive frames. So we can always estimate the optical flow based on the difference. And this motion net learns how to map given a frame, then it outputs the optical flow of that image. So this model idea was interesting, but I don't know, it was one of the not really the key paper, but it's sometimes mentioned in the history of this video models. So I just added to introduce their ideas. And this is the end of today's lecture. So yeah, today we talked about a lot of models. Let's quickly review what we've done today. So we started the idea of the two-stream models and the fused model, which is the improvement of this idea, and then the TSN and the hidden two-stream models followed by that. So all of these 4 models explicitly learn both the spatial stream and the temporal stream separately, and in the end, they fuse the scores to output the final scores on the labels. In the next time, we are going to go over the 3D convolution-based models, which is called C3D, R3D, which R means ResNet, and T3D, I3D, and S3D, and X3D. So we are going to go over the 3D convolutional operations first, and then we will talk about these models. So that's it. Any questions?